Hello everyone, my name is Yuxi Hong. So today's topic is exploiting data sparsity in Markov Cluster Algorithm. So Markov Cluster Algorithm, also known as MCL, is one of the most popular algorithms in protein sequence similarity problem. It performs flow-based clustering on a sparse graph. Since the protein dataset is extremely large, range from gigabytes to hundreds of gigabytes, so HIP MCL extends its original shared memory-based implementation to distributed system. And NVIDIA GPU accelerators are also used to further improve the performance. However, it still has the high memory footprint and the communication cost at large, when running at a large concurrency. So our question is, are there any data sparse structure inside the data set that we can utilize to accelerate the computation by reducing the communication cost? So here's a visualization of the MCL iteration. Here the input of the sparse and iteration goes. Then finally it becomes the cluster information. So the input, the vertices are the protein sequence and the edges are the similarity scores. Here is the algorithm description. So it is an iterative algorithm, and it only has 3 main operations inside this iteration. So the first is called expansion, which is sparse matrix multiplication. The A is the corresponding sparse matrix of the sparse graph. It performs random walk to enable the connection between the different regions of the graph. And then we're pruning to remove the low probability items. And the inflation is just taking the power entry-wise to strengthen the intra-cluster connection and weaken the inter-cluster connection. So among these 3 operations, the expansion is the most time-consuming step. So that's why we want to further optimize it. So since the operation is a SPGEM, sparse matrix multiplication, I would like to briefly introduce the 1D, 2D, and the 3D MPI processor layout in the distributed setting. So HIP MCL, it uses block distributed matrices, which means matrices are split into 2D, and it is further used the sparse summa 2D algorithm. Every processor owns a part of the input and output matrix, and during the computation, it fetch and get the data from the other processors and finish the computation. So 3D MPI processor layout, so the processor is organized in a 3D qubit, and it proved that it has lower communication cost. And 1D MPI processor layout hasn't been used because we know that it has a higher communication cost. Another important operation that MCL does before the computation is called random permutation. Because the input of the data set is known to be load imbalanced. So it performs random permutation so that the non-zero elements across each MPI processors are relatively the same so that they can achieve a better load balance. Alternatively, our idea is it possible to condense the non-zero elements to a subpart of the matrix so that we can reduce the communication cost. Here is the visualization of our protein data set called virus. And I'm showing the block diagonal part, full block diagonal part. And clearly the blue part in the off diagonal are zeros, and all non-zeros are gathered in the diagonal part. So we can see even without any computation, you can see clearly there's a diagonal block pattern in the graph. So here's a further analysis of we call diagonal sparse pattern. For the 3 data set, the virus data set and the Archaea and the Eukarya. They are all protein data set. And you can see clearly that there are diagonal pattern inside here. So we take a step further to think, is it possible to gather all the non-zero elements towards the diagonal block as much as possible? And let's change our MPI processor distribution, because if we use this as input in the 2D processor grid or 3D processor grid, then clearly the off-diagonal part, the processor will have no work to do. So, but internally, alternatively, so 1D MPI processors each will own a part of the block diagonal. So if we can handle carefully that, we may distribute the workload to every processor evenly. So it turns out that graph partition algorithm can also help in this setting. So I'm showing 2 graphs. On the right is the natural order, so I didn't do any modification. But on the left is called so it's the graph after the graph partition, which means that I use a graph partition algorithm to partition into, for example, k parts. The k is number of processors, and evenly to distribute the flops here. Then you can see we can capture almost all the non-zeros and the flops inside this diagonal block. So which means it might help. It might works here, right? So since we are using the graph partitioner, so we want to know how much overhead that we pay for the graph partitioner. So it turns out all the graph partition algorithm can finish in our data set, can finish within 10 seconds, which is relatively acceptable. And we can further optimize this using the distributed algorithm. So after we choosing this, let's introduce the SPGEM 1D algorithm. So we choose the column by column formulation. So which means that you can think of the B as a concatenation of the column vectors, and each column vector is doing a matrix vector multiplication, so that the B is stationary. So B is the processors on here, and the processor 1 on this one, and processor 2 on the second column. And all you need to do is just to get the data from A to finish the computation of your current part. So here is the distributed settings. Suppose you have 4 MPI processors. Then you need to care. So here B is all the B matrix, sub B matrix that you needed. But what you need, you need all the A matrix for the computation. Here, this column by column formulator has a benefit because you don't need to care about the movement of the C, which is much higher non-zero element than the input. So further, there is one technology called remote direct memory access I'm using. I'm also, because I'm relying on the MPI one-side communication. So because when we try to get what we needed, the A matrix, we don't, for every matrix processor 1, 2, 3, 4, we can get the whole matrix A to our local memory, but we can also get what we needed for the computation. So here is the design for what we needed. So we project the needed columns of A, and then we generate a projection vector, and we get only the data that we needed to compute to our local data. So here's the performance of the RDMA-based SPGEM. So I'm comparing with our SPGEM 2D, so it's the baseline. And also I'm showing the SPGEM 1D RDMA implementation with or without graph partitioner. You can see if we didn't carefully to use the graph partition in this setting, so we may not have optimal, we may have a better performance compared to the SPGEM 2D. So each MPI process has 32 OMBMP thread, and so the graph partitioner is important for the performance. Okay. So for the summary, the protein data set has diagonal sparse pattern, and instead of using the random permutation as a standard setting, so we try to use graph partition method to restrict the elements in the diagonal block. And we further utilize the 1D processor layout, which is not optimal if in the analysis to adapt our algorithm. So also the RDMA technology is used. So the future work in this work include the integration of the SPGEM 1D into the HIP-MCR and benchmark the whole application. And also we want to test on the larger data set. Okay, thank you.